Let's take a look at some example exercises on how to calculate the thermal considerations for a particular design. Let's imagine that I have a BJT transistor with the following specifications. The maximum power dissipation is listed in the data sheet as being 2 watts at a nominal ambient temperature of 25 degrees C, and the maximum junction temperature comes specified in the absolute maximum, the abs max table in the data sheet as 150 degrees C. We are to find the following. First of all, the thermal resistance from junction to ambient temperature, theta JA. In order to do that, we are going to refer back to our electrical analogy for the thermal process, where power dissipation was equal to the delta in temperature divided by the thermal resistance. And so from that we can solve for our thermal resistance, J to A, and it's going to be equal to the difference in temperature from the maximum junction temperature to our ambient temperature, nominal ambient temperature, divided by the thermal resistance from junction to ambient. Divided by the power dissipation. We already solved for the thermal resistance. And so we will have Tj max was 150 minus ambient temperature of 25 degrees C divided by 2 watts. And that's equal to 62.5 degrees C per watt. Now the next is, if our ambient temperature were to increase to 50 degrees C, what will be our maximum power dissipation? So we expect it to be lower than 2 watts because we need to account for the power D rating as the temperature increases beyond 25 degrees C. And so we can calculate our new PD max using the same equation as being equal to the delta in temperature, Tj max, minus the new ambient temperature of 50 degrees C, divided by the thermal resistance from junction to ambient, theta JA. And so in this case it will be 150 minus 50 divided by 62.5. And that will give us a maximum power dissipation of 1.6 watts, so as we expected, lower than the 2 watts because of the power D rating. Then finally, if the ambient temperature is sitting at 25 degrees C and the device is dissipating 1 watt, what will be our junction temperature? We expect it will be less than the maximum because we know that at 25 degrees C, we should be able to dissipate 2 watts without exceeding the maximum junction temperature for the transistor. If we wanted to calculate it, we can do that. And we're going to use again our analogy where we have our power dissipation and then we have our thermal resistance from junction to ambient, and this will be the temperature at the junction and this will be the ambient temperature. Notice that the temperature goes dropping, it's higher at the junction and then lower at the ambient. And in this case, theta JA represents the equivalent thermal resistance already from junction to case and from case to ambient. And so we can calculate, we wanted to calculate Tj. Again, if we use the electrical analogy, we know if this was a voltage, we will calculate this by calculating Ta plus the voltage drop, or in this case the temperature increase through that thermal resistance, which will be equal to Pd times theta Ja. And again, notice the electrical equivalent. If Tj was a voltage that we wanted to find, that will be equal to the voltage at the node labeled Ta plus the current flowing through the thermal resistance times the thermal resistance. So our new Tj will be equal to the ambient temperature 25 plus power dissipation is 1 watt times the thermal resistance, which is 62.5. So that's equal to 87.5 degrees. Let's take a look at another example, which is going to illustrate how we're able to operate a power transistor at a higher power dissipation with the use of a heatsink. Let's imagine in this case that we have a power MOSFET with a rating for its maximum junction temperature of 150 degrees C. And then we're given several values of thermal resistance. Let's assume initially we are not using a heatsink, and in that case we will have the thermal resistance from the junction to the case as being 1.75 degrees per watt, and from the case to the ambient as 50 degrees per watt. If we are using a heatsink, then we will have to take into account the thermal resistance from the case to the sink, which is 1 degree C per watt, and from the sink to the ambient, which is 5 degrees C per watt. And let's assume that the ambient temperature is sitting at 30 degrees C. Now we can see that the heat dissipation is going to be more efficient with the use of the heatsink by simply looking at the numbers, the thermal resistance numbers, when you're using a heatsink, and noticing that they are much lower than the top numbers when you're not using a heatsink, that theta C2A is 50, as opposed to 1 plus 5 at the bottom from case to air, but through the heatsink in that case. So let's go ahead and calculate, first of all, what will be the maximum power dissipation allowed for that transistor when we are not using a heatsink, and then what will be the maximum power dissipation allowed when we are using a heatsink with those particular thermal resistance values. So in the first case, we will write our PD max using our electrical equivalent equation will be equal to delta T, Tj max minus the ambient temperature, divided by the thermal resistance from junction to ambient. And since we are not using a heatsink, it will be from junction to case, and then from case directly to ambient. So in this case, it will be 150 minus 30 divided by 1.75 plus 50. Comes out to be 2.32 watts. And now, if we add the heatsink to the transistor, if we wanted to calculate the maximum power dissipation, we have essentially altered our thermal characteristics for the circuits by lowering the thermal resistance. So we'll have Tj max minus Ta divided by theta from junction to case plus from case to sink, now with a sink, plus from sink to ambient. And this will be equal to 150 minus 30 divided by 1.75 plus 1 plus 5, which is equal to 15.5 watts. So we can see a dramatic improvement in our maximum allowed power dissipation before we get to the maximum junction temperature allowed for this transistor. Now, if we wanted to calculate what's going to be our final temperature at the case and at the sink, let's imagine when this transistor is operating at its maximum power dissipation, meaning the junction temperature is sitting at 150, the ambient temperature is sitting at 30. So essentially we have this as our circuit. Our PD is sitting at its maximum, 15.5 watts. We have our 3 thermal resistances. From junction to case is 1.75 degrees C per watt. From case to sink is 1 degree C per watt, and from sink to ambient is 5 degrees C per watt. We know that the temperature on the junction under maximum conditions is going to be at its limit, 150 degrees C. The ambient temperature is going to be 30 degrees C, and we want to find out the temperature of the sink and the temperature of the case. So the temperature of the sink is going to simply be equal to Ta plus the power dissipation times theta from sink to ambient, which is going to be equal to 30 plus 15.5 times 5, which is equal to 107.5 degrees. And finally, our case temperature is going to be equal to our sink temperature plus PD times theta from case to sink, or 107.5 plus 15.5 times 1, which is equal to 123 degrees C. So this is equal to 123 degrees C. And so we can, as we expect, observe that the temperature goes increasing. For an ambient temperature of 30 degrees C, temperature of the sink is 107.5 degrees, the temperature of the case 123, and the temperature at the junction is 150. So the temperature goes increasing the closer we get to the junction. And so this is a good example for how the power dissipation increases by the addition of, in this case, a heat sink that allows to more effectively dissipate the heat. Thank you.